Just dive in and do it real quick. Just think with me for a second. I think it'll help to see the reason why. What if you wanted to solve that for x? You know, because we'll see maybe on next Tuesday. If not next Tuesday, then for sure the week after the test, we'll see real life situations, there's tons of them, where you end up with equations like this with x up in the power zone. We'll see biology examples. We'll see a lot of financial examples. Economics all the time. So anyway, so x up in the power zone like that, which is called exponential, huh? That's an exponential equation. Remember what exponential means? Not just that it has exponents, but that it has x up in the power zone, right? X has climbed into the power zone. So anyway, so how do you solve that for x? Suppose you didn't have logs. That's how we're going to do it. It's logs. Try some other way. Let me give you a second. Try anything you want to get x alone there without using a log.
No. I see it.
What do you think? Anybody have any ideas? How can we solve for x? See the problem? It's weird to have x in the power zone.
You can't make the bases the same.
Yeah, if that was just, if the x is the same thing. If the x was just on the level, if it wasn't in the power, then I could just divide by 2, huh? Mm-hmm. But I can't do that. That's not 2. This is not 2 times x. It's not multiplied. It's 2 to the x power. I can't just divide by the 2. Yeah, and I can't make remember that hokey little method where we made the bases the same? I don't know if I called it hokey at the time. It was. You know, I mean, I know we did it and everything, but they were just giving you something fake until logs came along. Because, look here. You can't make 7.5 2 to some power.
No, you can't.
Right? Remember they kept giving us like really nice numbers, like 4. They go, 2 to what power is 4? You know, or 8. Well, try 7. Now what? You see how that was a hokey method? That was just goofy. That isn't going to really work. Real life, they do things with math, science. It isn't going to work. Where are we at? 7.5? It was 7.5. Anyway, so any other ideas? I think it's worth trying stuff for just a second to appreciate the role that logs play for us. How else are you going to solve for that x?
We would have to make the bases a fraction.
Yeah, right. What's that?
We would have to make the bases a fraction, and then we could have it to some power.
Like what kind of fraction?
I don't know. That was my only thought.
Abdul, you have a method?
Can you be like multiple log?
Yeah, we're going to do log.
Yeah, two sides like.
That's what we're going to do. But I want to try without a log. I want to show that we need log by showing you how you cannot do it without a log. Nothing else will work. This is exactly what was experienced by people as they were doing real life. You know, they're doing real life economic problems, biology problems, and they're like, "Hey, x is up there in the power zone. I need to get x alone. You know, I'm trying to solve for x, and I don't know how to get x out of the power zone. What am I going to do?" That's why they made up logs. That's literally what they did. They said we need to make something up that's the opposite of exponentials because we got to get that thing out of the power zone. That's literally what they did.
So
They made it up because they needed it.
there is no other method?
Right? There's nothing else that'll get x out of that power zone. Yeah, you know what it's like here? You guys had trig, right? Mm-hmm. And you remember it all perfectly, right? No. We'll review it the last 3 weeks. But what if you had cosine of x is, I don't know, cosine of x is a half. So how would you solve for x there?
The inverse.
Can you divide both sides by cosine?
No.
Yeah, I hope you know that's no. Because that's not multiplication. That's not multiplication, is it? That's like a function. That's like f of x. All these things are functions. Sine, cosine, tangent, logs, exponentials. These are all functions. Well, that's why I made up the whole toaster talk. Because I saw that people were looking at that when I first taught calculus, when I was kind of fresh out of college and I started teaching calculus. I saw that everybody was looking at that and thinking that that was multiply. And I was like, ooh, that's going to hurt them. They can't be thinking that's multiply. That's not multiply. So that's not multiply. That's function. That's like in a function. That's why I made the in the toaster kind of talk. It's inside of something. It's not just sitting next to it. It's in there. So what do you do then? If you can't divide by cosine because it's not multiply, how do you get rid of that cosine?
You memorize, and you know that cosine.
You do cosine inverse. Cosine inverse. I know half's a nice one, but if I give you one that's not half,
Yeah, no.
like square root of 7 over 8, there's no memorized to it. You'd have to do cosine inverse. The inverse function gets rid of the regular function. Well, that's exactly what we're doing here with these exponents and these logs. Does that make sense? When you look at this 7.5 equals 2 to the x thing, you've got to just know that the only way to get that x out of there is the opposite function, the inverse function. And what is that? Logs. So logs are the inverse. Now, so I'm going to do a log on both sides. You know what it's like? It's just like if you had square root of x equals 7 or something. How would you get rid of that square? You want to turn that into regular x. How would you get rid of that square root? 2 power both sides, right? Because those cancel, don't they? They're opposites. Same, vice versa. If you had x squared equals 9, how would you turn that into regular x and get rid of that 2 power? You would root it. Root it on both sides and do plus or minus. Because rooting and squaring, again, either way you go, they're opposites of each other, aren't they? So they undo each other. Well, that's exactly what logs and exponentials are like. They're opposites. Logs were made up. Their definition is, their whole role in life is we're just the opposites of exponentials. That's exactly what they were made up to be, the opposites of exponentials. So, all right. So now every log has a base, doesn't it? There's no such thing as log without a base. So which base am I going to put down here on this guy? Yeah, whatever base that your exponential problem has, which is 2. Log base 2. You got to make those match. The base of the log, the base of the exponent must be the same for them to cancel. Right, you with me? That making sense? So that's just like when you have, if I had x cubed here, if I had x to the 3rd power is 7 or whatever, what root would I need to do to get rid of that? 3rd root on both sides, right? Same thing. Whatever your base is, do the log of that same base on both sides, and then what will happen? They will cancel. These will cancel, just like these cancel. And the x is alone, log base 2, 7.5, we're done. That's all they want for now. So they just want you to translate and get x alone.
Just for now, right?
Just for now. They're going to ask for more in a second.
I was going to say, I got the almost exact same answer.
Okay, now we're saying, hey, can we get rid of that log? Now we've got a log. See the difference? The last problem, we didn't have a log. We had an exponential situation. We wanted to get that x out of power. Now we have a log. We want to get rid of that log. So what they'll say is they'll say change to exponential form. Change, so we're changing languages from 1 to uno kind of thing. So what do I do to get rid of that log base 2? 2 on both sides, huh? So remember, the bases must match. The base that you're doing the power with and the base of the log must be the same, and then they just cancel. They're opposites. By the way, notice I'm not putting that 2 next to the log. And it's not up there next to the 4 on the other side. It's down on the ground. It's a base, huh? Right? It's got to be a base and a base. And so then you get 16 is 2 to the 4th, which we're like, yeah, we know that. Well, the log is like, that's what I was saying all along in my weird little language. Is that making sense?
So, C.
Log base 2. Let me say one other word, because I know sometimes it just really seems weird, and people are like, that's just weird. Let me help. Another way you could think of it is log. When you see log, you could think of the phrase or the 2 words, power needed. That's another way. That's really what log is doing. Instead of giving a power, which is what exponents do, it's doing the opposite. It's asking for a power. So it's saying, what's the power needed on a 2 to become 16? That's what log is really saying, if you want something to more grab your hands around. Power needed on a 2 to become 16. Power needed on a 2 to become 16. What power is 4, right? Equals is. Power needed on a 2 to become 16 is 4. The power needed on the 2 is 4 to become 16. See, we get the same thing? That's what logs are really saying. Power needed. They ask for a power rather than giving a power. They're the opposites of exponential. Okay, so now on this one, we want to actually solve. So in other words, it's not just a matter of changing form. We got to actually solve. Every log, there's 3 parts to a log expression. There's a base, there's the thing that comes right after the base, the plug-in or argument, and then there's the other side. I don't have anything on the other side, so call it x. Call it x. So just call that x. Now, there's 2 ways you can do this problem. You could just read it if you can read logs. Well, what does the word log mean?
The
Power needed.
On a 4 to become 1.
Power needed on a 4 to become 1. That's what it says. That's what log says. What's the power needed on a 4? It's the power needed on a 4 to become 1. 0. That's the answer. Answer is 0. Now, I'll also show you more formally. That'd be the informal, kind of casual way. Doug.
I just answered that, and it said that was wrong. Did I format it wrong, or?
Did you just put a 0?
No, I put the number, it's log 9, 1 equals, and I put 9 to the power of 0. It said that
No, it's just 0 straight.
okay.
Just 0 straight. All right, so the more formal way would be to, how would you, so I showed you kind of casually, just read it. The other more formal way would be to do the base, right? 4 on both sides, like that. Boom. Right, because again, if the bases match, they cancel, so 1 equals 4. See how that's the same question we were looking at a minute ago? 4 to what power is 1? So what does this have to be? Can we solve by observation? 4 to what power is 1? What does the power have to be? 0. That's the answer to the question. That's what x is. X is 0. There we go. Is that good? So either way, formal or informal. Let's try another. Log base 1/3 of 27. So try that one. Formally, I would go equals x, and then get rid of the log word by doing the base on both sides. You can do it either way, formal or informal. So if I'm going to do it the formal way, I would do the 1/3 on both sides. The informal way would say the power needed on a 1/3 to become 27. That'd be the informal, right? Power needed, that's what log means. Log is power needed on a 1/3 to become 27. But anyway, I'll do it the formal way. These cancel. Right, when the bases match, those cancel, and you get what? You get 27 is 1/3. See how that's the same question? I just put a question mark here and an X there. Same thing. All right, so now, what is that power?
-3.
Yeah. Yeah, do you remember? Excuse me. Excuse me. Excuse me, yeah. Okay, if that was just a regular 3, instead of a 1/3, what power would we need on a regular 3? 3 to what power is 27? That'd be 3, because 3 times 3 is 9, times 3 is 27. That'd just be normal 3. But we have 1/3, so you got to get that 1/3 to flip, huh? What flips? Negative, so it needs -3, doesn't it? The negative part flips it over to be 3 over 1, 3, and then third power makes it 27. Remember that negative powers flip things? So then the answer is -3. We good there? Questions I can answer on that one? Now, I want to also show you guys have your calculators with you? I want to give you a backup plan with your calculators. Yeah, let's talk about calculators for just a minute. Let's redo this question. Log 1/3, 27, that was it? Yeah. Okay, now on your calculator, you'll see 2 log buttons. Just regular LOG. Let me write that here. Regular LOG and then LN. Those are both log buttons. every log has a base. Neither of those is showing like a number like 7 or any kind of number as the base. So what does that mean? What is, if they write the normal log word, that means, yeah, you remember this from your algebra days? Base 10. Yeah, it means base 10. It's called the common log, which means it's the one used most commonly in science applications. So you know how that works, just like any other field. You know, like if you do cube root, you have to write the 3, cube root of, whatever, 27. But if I just write a normal root like that, and I don't put anything in the hook here, what does that mean is really in the hook? 2, right? Remember, we call it a square root. But we don't write the 2, do we? We just, why? Because that's the one we use most of the time, huh? So we just say, look, if I don't write anything in the hook, I mean 2. Because that's the one I use, 99% of the time. If I'm going to use any other number, I'll write it. Well, that's exactly what they did with logs. In real life, they used base 10 so often that they just said, okay, that's the common one. If I don't write any base, I mean 10. Because every log has to have a base. There's no such thing as log without a base. Now, there's also ln. Anybody know that one also has a base?
That's a natural log.
Yeah, it's called natural log. And what's its base?
E.
It's E. Yeah, that one has a log of base E. E being that special number, that you'll learn more about in calculus, 2.718, blah, 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 blah. We discovered it naturally. It's the perfect number who's its own derivative. Anyway, they're doing real life things and they found it naturally. So they call the log that has the E, the naturally occurring number as its base, the natural log. Why is it backwards? Why is it ln? Doesn't that... Should it be NL, natural log?
Logarithmic natural
Because
log.
logs are bad.
Because logs, all right. That's a creative answer, Doug. I never thought about that. It's because the French came up with it. A lot of algebra was discovered by French. And what do I mean by that? I'm not putting down the French, although there's many reasons to do so. Is that inappropriate? But anyway, I'm listening to Napoleon Bonaparte's biography now. I'm a wannabe history person. So he's a rascal. He was a genius about battles, but
That's like the
he's rough.
way to describe Napoleon.
Yes. Anyway, I'm getting off topic. So it's just because in those romantic languages, they say the adjectives after the nouns. That's all I'm pointing out, right? Spanish, French, all those romantic languages, Italian. They always say the dog blue instead of the blue dog. They do it wrong. No, I don't know. It's just different language, different way. So that's all they're saying logarithmic, natural. French people came up with. Anyway, natural log. So anyway, it means natural log. There we go. Log base E. There it is. Okay. So my point is every log has a base. These are 2 that don't show their base, but they really have a base. They write the normal log word, and they don't show the base. It's 10. They write ln, logarithmic natural. The base is E, the naturally occurring number. All right. So with all that said and done, how am I going to do log base 1/3? I don't have a button for that. There's not a log base 1/3 button. All we've got is the regular log button, which means 10, and the ln button, which means base E. How do you do base 1/3?
So,
Or any other base other than 10 or E? How are we going to do all the millions of logs that have bases that are not 10 or E?
if you do the log of 1/3, the x comes out in front, and then you do the log of 1/3, and then you divide by log of 1/3.
I don't want anything that hard. Anybody know a quick, simple, bang, bang way?
Put it in the calculator.
You make it 2 logs. So I want to show you this rule. You make the top one go top, and you make the bottom one go bottom. You make it 2 logs. Now, it's a special rule. I don't have any time to tell you why that's true today. Be glad to show you office hours. Maybe on practice exam day. Probably never show you why. But we just don't have time. But I'd love to. Come to office hours, I'll show you why. You can prove that's true. But anyway, there it is. Like magic, it's called the change of base formula. Why? Because both of those logs are really base 10 logs. I'm not showing a base, right? So they're 10. You don't have to write that 10 in there. But I'm just letting you know, look, we changed base there. Did you see that? It was a base 1/3, and I made it into 2 base 10 logs. It works. It's true. You can prove it. I don't got time. So anyway, that's how you do it in your calculator. So if they're giving you a log of some base that's other than 10 or E, you can do it on your calculator. I want to give you a backup plan so you don't have to do the X and all that kind of stuff. In fact, we'll have to do it in a little bit. We'll have no other way. So want to check that out real quick? Hit the buttons on your calculator. You should get the -3 answer we got a minute ago with the x and all the other stuff we did. Is that making sense? So you just make it into 2 logs, and a lot of people have asked me over the years, Mr. how do you know which one goes on the top and the bottom? Notice the higher up one, the one on the top, goes on the top, and the base one, which is lower down, goes on the bottom. Top goes top, bottom goes bottom. Make it 2 logs. That good?
That's called change of base.
It's called the change of base formula because we changed from log base 1/3 to log base 10s.
Is that written somewhere up there? Or?
No. Yeah, you don't need to know the name. I'm not going to quiz you on that. There could be some that you can do by hand on the non. Yeah. All right, so try that one. How about we do the x way first? And then you can do the buttons on your calculator to verify. So just go equals x. You know how to get rid of the log word, right? You know how to translate out of the log language. So take it from there, see what you can find.
The log is a piece of wood you find in
All right, so if we want to do it by hand, what are we gonna do to get rid of the log word? Bases must match. So I'm not doing it that way. I'm doing it by hand, not by calculator. I'll do it by a calculator at the end to verify.
You do
Root 6, and these will cancel. That making sense? So if the bases match, the base and the log will cancel. So that would bring us down to 36 is root 6 to the x. Good so far? So this would be the by hand method. We'll do it by calculator also to verify our answer. Now, can you tell from there? Can you solve by observation, so to speak? Like what power, how many root 6s do you need to make 36? Yeah. So because 2 root 6s make a plain 6, 2 more make another 6. 6 times 6 is 36. You need 4 of them, huh? So everybody see that power has to be 4? Right? Because remember, 2 of them is root 36, which is plain 6. 2 more is another plain 6. 6 times 6, that makes your full 36. You need 4 of them. So the answer should be 4. X is 4. Now, did you try it with your calculator also? Try, remember how to, so by calculator, I don't know if I have room here, by calculator, the top goes top, the bottom goes bottom, so hit log of 36 divided by log of roots, right? You make it into 2 logs. The top goes top, the bottom goes bottom, you should get 4. Same answer, 4. We good with all that? Questions I can answer? So by calculator or by hand? All right, I'll move on if you're okay. A period. So let me remind you. Let's do the whole domain story right here. So domain. What does it mean to find domain? It's allowable x values. Remember, I always make the analogy of like a microwave. Things you're allowed to put in. What are you not allowed? You shouldn't put tinfoil in a microwave, right? So we're looking for what you shouldn't put in to various functions, like not putting tinfoil in a microwave. So we had a few no-nos, right? We have, well, up to now we have 2. We're going to add a third now. No-no. Something you can't do with logs. So what was our first no-no?
No zero. Yeah.
No zeros in denominators, right? Denominators cannot be 0 because dividing by 0 is infinity. It's undefined.
inside of square root?
Inside of a 2 root, yeah.
Must be more greater than 0.
And not for 3 roots, right? Everybody good there? 3 roots, you can have negatives in a 3rd root, huh? That's fine. But not for an even root. So inside, yeah, the inside has to not be negative, right? Because the square root of a negative number is imaginary. Remember that? So you can't have that. How do you write in math symbols not negative? Greater than or equal to 0, right? That's not negative.
I flashed over the chocolate.
Greater than 0, equal to 0, right? You can be 0 or you can be bigger than 0. That way you're not negative. Now, that's what you already know. Here comes the new one. When it comes to logs, we have this new thing we've made to be the inverse of exponentials, log, it turns out the inside of a log has certain requirements. The inside of a log has to be not negative also, just like the inside of a root, but also, more than that, not 0. So the inside of a log is even more picky. Not only can it not be negative, it also can't be 0. You can try that in your calculator. Hit log of negative something, whatever, and it'll go error or domain error or some kind of error. So log of any negative, or 0, try 0. Log of 0, it'll also give you error. So we can't put 0, we can't put negative. So how do I write in math symbols? Not negative, not 0.
Greater than 0.
Greater than 0. Yeah, positive only, huh? Greater than 0. Not equal, right? It doesn't have the equals bar like the inside of the root can be 0, so we have the equals. But inside of a log, just greater than 0. That's it. Those are the 3 big no-nos for domains. And that's it, like, that's all I know. I mean, through calculus and beyond, there's really nothing else to add to that list. Those are the 3 things you look for to watch out for domain problems. Okay, so if we got those down, let's look at number 8. So number 8 is giving us this function, log base 3 of x to the 7th, and they're saying to us, find the domain. Find the domain. So what have we learned to do? You take the inside, and you say, hey, inside you have to be positive only. Not negative, not 0, so greater than 0, huh? Positive only. So what is the inside? Like when I say inside of that log, what do I mean inside?
X.
This x to the 7th. Right? Anything after the base. The base is the 3. That's not inside. The whole x to the 7th has to be greater than 0. Now, think with me just logically for a second. If I said, hey, guys, I have a number to the 7th power. That's what x to the 7th is. It's got to be greater than 0, which means positive. Right? I think if I just say positive, easier way to think about it. So, say, hey, I got a number to the 7th power, and I need it to come out positive. What does that mean about my number itself? What kind of numbers to the 7th power come out positive?
Positive numbers.
Positive numbers, right? That just means the number itself's got to be positive. And then it to the 7th power, right? Because if you take a positive number and you multiply 7 of those together, it's going to be positive still.
But also, since 7 is an odd number, if you have negative numbers, what do they come out? Oh, look at that.
So it's all good, right? So that just means the number needs to be positive. So the number is positive. So we would say all positive real numbers. Now, there's other versions of this question. So let me show you. You might not get to the 7th. You might get log base 3 x to the 6th power. So how would that be different? Well, take this over here. Inside, and that's x to the 6th. Greater than 0, positive. So what does that mean about x? Let me let you think about it. Think about it careful before you say. Think about it careful. What does that mean about x? If I say, hey, I've got this number. I'm going to take it to the 6th power, and I need that to come out positive. What does that mean about my numbers? What kinds of numbers to the 6th power, 6 of them multiplied, come out positive?
Just not 0.
Yeah.
Just not 0. Any number that's not 0. Right? Could be negative, because negative 6 times, right? An even amount of negatives is positive, isn't it? So it could be negative or positive. Either way, 6th power, it'll come out positive as long as it's not 0. That's the only one that'll just be 0. So that in that case, it'd be all non-zero. If you get an even power on this question, see how it's any number to an even power comes out positive as long as it's not 0. That good? All right. So grab the in. There's the inside. Natural logs, no difference, just another log, but base E, right? Say, hey, inside, you have to be positive. So 1 over x. I'm just going to write the word positive. I think it might be easier for you to think. You can write greater than 0 if you want to, but I think you might be able to think a little better if I just write the word positive. So if I say, hey, I need that thing to be positive. So what does that mean about x?
It also has to be greater than 1.
Yeah, because the top already is positive, huh? So we just need the bottom to be positive, right? If you have a fraction, the top's already positive. You just need the bottom to be positive, then positive over positive will be positive, right?
Except for class 1.
So yeah, the bottom's got to be positive is what that means. And positive means greater than 0, so x has got to be greater than 1. Make sense? As long as x is bigger than 1, that'll work. We good on that? See how I thought that out? So fraction to be positive, the top already is positive, the bottom's got to be positive as well. Positive over positive will be positive. So for the bottom to be positive, positive means greater than 0. Then I just added 1 to both sides. X is greater than 1.
It's saying that's not right.
It's lying to you, Doug.
You have to put it in,
Read that. Oh, it does. It says interval notation. I should have read the fine print in the contract. Yes, so we got, how do we write that interval notation?
Bracket 1 to infinity.
Parenthesis, huh? Because bracket would be touching the 1.
Oh.
Yeah, we want a parenthesis, not a bracket, because we're not equal to the 1. Yeah, interval notation. I signed the contract without reading. We all do that, right? Every time we do something with a website and they have that big long list, license, you don't read every word, do you? Right in the middle it says, and you'll give your first 3 children to the company, you know, whatever. I agree. Just give me that app, whatever. All right, so let's try this one. Calculator? So try that one. Natural log of 67. So just hit the buttons to just make sure you can do your sketch calculator. Let's try this. You have an LN button. That's LN. I know it looks like IN. I don't know why they do that, but it's LN. I guess it's the French again, huh? Those crazy French. All right, LN. There's an LN button on your calculator. So right below log or next to log. So LN, what should you get here? LN 67 divided by 35. I'm getting 0.6. Yeah. They want 3 places, so there we go. It's 0.6493, so you round to the third place, 0.649. Y'all getting that okay? Okay, now the number 11 is a little more tricky. As we do number 11, let me say something about just normal fractions. Number 11's got a real good lesson for us for more than just logs. If you were going to do 1 plus 2 over 3 plus 4 in your calculator, I mean, I know you wouldn't. You can just do that by looking at it. But what I want to point out is if you were to type into your calculator, divided by 3 plus 4 like that, it wouldn't do what you want. It would only divide those numbers in the middle. You see? Because it doesn't really know you mean the whole 1 plus 2 is the top of the fraction and the whole 3 plus 4 is the bottom. How would you fix that? How would you make it do what you really want? You'd have to put parentheses there and parentheses there, wouldn't you? So that's what we see. You have to put parentheses here and parentheses here. So whenever you have more than one, in fact, let me rewrite. So it'll happen in the future stuff we're going to do week after next. When more than one item in the top or the bottom must parenthesis around it. So when there's more than one, if there's just one thing in the top or the bottom, doesn't matter. You don't need extra parentheses. But if there's a couple of things, 2 or more, you got to put parentheses. That way the calculator knows it's a grouping symbol, really. It says this group hangs together in the top and this group hangs together in the bottom. That's what it really is. Now, when you type that in, go ahead and type that in, get a number. I'll get a number 2. It's going to also give you little parentheses, right? It automatically puts parentheses around the numbers. So you see, this is what it's going to look like on your calculator. So you see how you'll close with double parentheses after the 4 on the top there? The parenthesis to close the 4, then the parenthesis to close the whole numerator. You see? So see what you can get there. I'll try it too. I'm getting a 2.30, yeah, 2.5. You're both round to third place, so that 2, look 1 to the right, 5 or more goes up. So 2.303. Is that coming out okay? I'm Glad to help you. A couple people grabbed me after the last class. We're having trouble getting their calculator to do that. So I'm glad. 10 seconds. I can help you with that. So grab me after. You want to be able to get those on your calculator. We'll do a lot of those in the future. All right. So let's move ahead. We're going to do some graphing now. So if you have y equals log base b of x plus c, and I'll just put a plus d out there that really doesn't matter much, that number in the parentheses, negative c, is the vertical asymptote. So coming back here to negative c, and then the graph just goes up like that. It goes up to the right. Now I'll be talking about the direction of these graphs a lot. So I want to be real clear with that, because you might look at that graph and you might go, well, why, Mr. Heron, are you saying that thing goes up to the right? I mean, yeah, that part goes up, but this part goes down. So what do you mean? So I'm not talking about the vertical asymptote. They always, on the vertical asymptote, we know that any graph follows its vertical asymptote, right? They always go down forever or up forever at a vertical asymptote. I'm not talking about that. That's just always happening. I'm talking about the other side. So whenever I talk about the direction of the log graph, I mean the other side, not the vertical asymptote side. That always just goes along the vertical asymptote. So this one goes up to the right. And the number in the parentheses next to x, opposite of that, becomes where the vertical asymptote is. Okay, so let's see what we can do about graphing. Let's try. So, all right. So the first thing you want to do here on number 13 is got our vertical right there and got our graph there. Oh, by the way, let me this is log, right? Well, here. Let me do one more thing actually before I go there. I'm going to go down here real quick and show the exponential graph. Again, you know the exponential graph has a horizontal asymptote, and it goes up to the right. I just want to point out, both graphs go up to the right forever. Log, and this is exponential. This is y equals a times b to the x plus c. This horizontal asymptote's up at c. So there's exponential graphs, because today's all about log and exponential and how they're opposites, and this is log. So notice both graphs go up to the right forever, but they do it very, very differently, don't they? Very, very differently. Notice that, what that difference is, how we say that when you get into calculus, is we say that's concavity. Meaning the log is like a bowl turned down. See how this looks like a bowl turned down? Even though it's going up, it's concave down. We talk about concavity. Whereas the exponential graph, it's a bowl turned up, isn't it? It's concave up. Whereas this one is, the log is concave down. So that's very different going up styles, right? They're both going up forever, but the log is going up super slow. It's really slow growth. It's not getting up very fast because it's like a bowl turned downwards, even though it's going up. And exponential, he's rocketing up because he's not only going up, he's going up faster and faster and faster. He's like a bowl turned up. That's concave up. In calculus next semester, if you take that, you'll learn that that's the second derivative, which tells you the concavity. The first derivative tells you if it's going up or down. The second derivative tells you if it's concave up or concave down. You learn about that kind of difference. Will start to become more and more important. You learn about how curves bend different and some of the different things they do. And derivative will tell you all that. Derivative is like amazing. Tells you everything about a function almost. That's next semester.
I'm scared.
Oh, it's good stuff. All right. So now let's go back to this one. So looking at this one then, so what you want to do is you want to start here and go, okay, I know the normal log, has his vertical and goes like that. That's the normal log, if there's no flips of any kind. So normally they go up and to the right. So what does this log do? Which direction? Now when I say direction, Do I mean this side or do I mean that side? Which side? I don't mean the vertical asymptote, right? We know they always go along the vertical. I mean the other side, the non-vertical asymptote side. So that side is going where? It's going up and left, huh? So it's been flipped somehow. Has it been flipped sideways or up and down? Sideways. It's been flipped left, hasn't it? Because it was going right. Then the original one goes right. They all go up and to the right originally. This one goes left. It's not been flipped down. It's still going up, right? Started up, still going up. So there's not been an up-down flip, but there's been a sideways flip, huh? Okay, so what does that mean about the equation that we're looking for? What does it mean when any equation has been flipped left? What makes that happen? Negative sign where? Negative on the x, huh? Because that's the sideways. And not a negative in the front of the log.
Negative on the front.
So negative on the x and not in the front of y. Because if there was a negative in the front of the log, that'd flip it down. Right? You with me on those? Remember x effectors, y effectors from a month ago? Remember that kind of stuff? So when negative is on x, that's a sideways, which is what, that makes it go left. That's what we've got. And if there was a negative on the front of the log, that would make it go down instead of up. But we don't have that. All right, so here we go. Could it be A? What are we looking for? We're looking for a negative on x, not on the log. No, A does not have a negative on the x. Could it be B? No, B's got a negative in the front, not on the x. Could it be C?
Maybe.
C's a maybe. It's got a negative on the x. Looks good. D?
Maybe.
Yeah, it's got a negative on the x. Looks good. E?
No.
No way. Negative on the log and not on the x. No way. F?
No.
No negative on the x. G? No negative on the x. H?
Maybe.
It's got a negative on the x, but it also has a negative on the log. That would be down and left, wouldn't it? And so, no. So we're down to C and D. Now, normally at this point, we get it down to 2 and we make a table, huh? And we could do that. You can make a table, but actually we have another thing that'll make it even quicker. Look for the vertical asymptote. Now, where is our vertical asymptote? Well, it's at 0. It's at 0. Which means, now where's the vertical asymptote in the equation? It's the number in the parentheses next to x. Right, the opposite of it is where the vertical asymptote is, huh? So what's the number in the, so if x is 0, what we should have in the parentheses is nothing. So it's C. It can't be D. See, D has a 1 in the parentheses. D is really saying, see what D is saying? It's saying log base 2. Here, let me try to write it a little better. It's saying log base 2 of minus x plus 1, isn't it? And that would mean it would have a vertical at -1, wouldn't it? That's not right. We have a vertical at 0. Everybody good? We've got it. All right. Let's try number 14. Think about flips and stuff. Look where that one's going. Try to go through your list and try to eliminate a bunch of things. Okay, so where's this graph going? This side, I don't mean the vertical asymptote side, huh? Because they always go to the vertical. I mean this side, which is down and right. The normal graph goes up and right, huh? Like all of them. All of them go up to the right, normally. So how's it been flipped?
Negative on the log.
Flipped down, right? Because it's going down, but still going right. So it's been flipped down, so we have that. What does that is a negative on the log, not a negative on the x, huh? So we're looking for an equation that has a negative on the log. That's what makes it go down. That's why it's going down. But not a negative on the x, because that would be left. We good? We'll go through it. So could it be A? No negative on the log. Could it be B?
Maybe.
It's got a negative on the log, not on the x. Looks good. We'll come back to it. Could it be C? No. No negative on the log. Could it be D?
No.
He's got a negative on the log, but he also has a negative on the top. That'd be left and down. That's not right. E.
No.
No negative on the log. F.
No.
No negative on the log. G.
No.
No negative on the log. H.
Maybe, but
Perhaps.
it's not.
Yeah,
Yeah, maybe.
it's not.
Maybe. All right, so we're down to B and H. They both have negative on the log. They're both going down. And they do not have a negative on the X, so they're going right. Down. They both go down and right. So, what do we do? Well, we could try the vertical asymptote thing, but they both have the same vertical asymptote. Right? There's nothing in the parentheses next to X for either one, which just means 0, and that indeed is where our vertical asymptote is. So they both also match the vertical asymptote of 0. So we're going to have to make a table at this point to find which one's right. Does this make sense? Tracking with me? They both have nothing in the parentheses next to X, which means 0, vertical asymptote, which is correct. So we got to make a table. So let's come up here then and make a table. So you just grab one of them and make a table. Like I'll just grab the first one here, B. Try him first. So take X, Y. Now start with 0. If you plug in 0, you get Y equals negative log base 2 of 0. Now, what is that? I mean, what number? How do you figure out what number that is?
What exponent is necessary to make 2 into 0?
So use your calculator, and I would just let the high go high, the top one go in the top, let the bottom one go. Remember, you just use your calculator. That's why we learned that. For such a time as this, right now. So let the top one go top, let the bottom one go bottom. Hit the buttons on your calculator, and you'll get an error. Remember, you can't put 0 in a log.
Oh, that's right.
So that top is air.
What was I trying to do with that?
So that's no. Now, is that correct information? At 0, yeah, there's a vertical asymptote. Of course it's no. You can never touch a vertical asymptote. That's why there's one there. Because the log says no. All right, well, let's go to 1 then. So minus log base 2 of 1. So again, put it in your calculator. Let the top go top. Let the bottom go bottom. Hit the buttons on your calculator. You'll get 0. Because the top is 0. Log of 1 is 0. So that's 0. Is that a true dot on the real graph? Over 1, up 0. Beautiful. Yep, that's our graph. See how that point is hitting the graph? It's on the graph perfectly. Over 1, up 0 is right on the graph. So that's it. We've got it.
So it would be?
The answer is B. If you tried H, if you plug that in, you'd get a point that doesn't work on the graph. You can do it real quick. If you tried H, maybe I shouldn't use up too much time, but if you did 0, you'd get no. That's all the same. If you did 1, you'd get 1 minus log base 2 of 1, and that would be 1 minus log 1, the top goes top, bottom goes bottom, and that'd be 1 minus 0, that'd be 1, it'd be 1, 1. 1, 1 is not on the graph, that's here. You'd get 1, 1, which is not a true point on the graph. H is not right. Is that good? So eliminate everything by the flips, get 2 left, try looking at vertical asymptote, but if they still persist, make a table. Flips and all that. Think about which way it goes. Give you a second. Okay, so what are we going to do? So, well, first off, which way does this one go?
It's up and right.
Up and to the right, huh? Up and to the right. So has it been flipped at all? No flips. It's going up and to the right, which is what they normally do. This is no flips. Up and to the right is normal. It's not been flipped left. It's not been flipped down. Up and to the right. No flips, which means what? No negative on the log.
No negative on
And no negative on x. Let's go through. Could it be A? Got a negative on log? No. Could it be B? Yeah. No, there's no negative on the log. There's no negative on the x. Could it be C? No, he's got a negative on the x. Could it be D? Negative on the log? No way. Could it be E? Negative on the log? No way. Could it be F? Negative on the x? No way. Could it be G? Yes. Could it be H? 3 yeses. So now we got 3 options. Can we eliminate any of them by thinking about the vertical asymptote?
G.
So we're going to. So the vertical asymptote is 0, which means you better have nothing in the parentheses next to x. Bye bye h. Right? Because that has a number in the parentheses next to x. That would mean vertical asymptote positive 1. So that's out. Okay, so now it's down to B and G. Now, are you aware that that -1 to the right of the B is not in the parentheses?
Right.
Yeah, let's talk about that for and I'll come back and finish this problem up. But that's really important. You know, you guys took trig, right? If they gave you cosine of x -1, obviously that's all in the parentheses, versus cosine of x, if they just write it this way with no parentheses, do you know this means the parentheses are only on the x. Are you aware of that for all functions? So same thing is true for log. If I write log of x -1 and I don't put any parentheses, that means only the x is in the parentheses, huh? Are you aware of that? That's really important, not just for logs here and now, but for on you go for calculus, with functions. So let me say it really clearly. If no parentheses are showing on a function, if there's no parentheses showing on a function, then it means only the item right next to it is in the parentheses. That's long-winded. I don't know how to say that a little better than that. But only the immediate thing. That's probably what I should have said. If there's no parentheses showing, then only the immediate thing is plugged into the function. That's why I made up all that toaster talk, because I realized people were having trouble thinking that way about functions when I first started teaching calculus. I would see people do stuff like this all the time. I'd see people take cosine of x -1 and cosine, and they just like cancel things and do crazy stuff. And I was like, oh, they do not realize that those things are functions, and that's different. And then anyway, so does that make sense? So you always want to think all these things are functions: sine, cosine, tangent, log, exponential. They're all like f of x. That's how you want to think about them. And there's stuff plugged into them, the toaster. And so this means only the x is plugged in, unless parentheses show you that there's more plugged in. Does that make sense? So if there's no parentheses showing, only the means. So right here, when you look at this log right here, you want to think only that x is in the parentheses, huh? Only the immediate thing right after the function is plugged in. Anything else is outside, which matters, because then that's a y effector, not an x effector. It has all kinds of different results. So that's very different. B is very different than H, huh? Because in H, they're telling you the whole x -1 is plugged into the toaster. On B, the -1 is outside of the plug-in. It's not in there. Yeah.
So then, we're looking for a negative x sometimes, right? And so we're like, when it flips, there's a negative x. But that, if it's in the parentheses, we're saying it's an active x effector as well. So x -1. But that's
Yeah, this is an x effector. That's not a flip.
It's not a flip.
Flips are multiply by negative, not add, subtract. That would be a move, right?
Okay.
Yeah, remember added, subtracted numbers move graphs, multiplied numbers by a negative, flip them.
Okay.
Yeah, that's right, good question. Yeah, so and that's why what would that -1 do? That would move it right 1. That's why the vertical asymptote is right 1. Remember, it's opposite. That's why we say vertical asymptote is always opposite of what's in the parentheses added, subtracted. Yeah, whoops. So that one's out. So what are we down to then? I've lost focus. B and G, right? We're down to B and G. They're both good. There's both nothing in the parentheses next to X, so the vertical would be 0. Same thing for G. So it's one of, how do we know which one?
You have to make a table.
Got to make a table. So let's try B. Let's just start with B. So start with B. Going to make an XY table. Going to plug in 0. Y equals log base 5 of 0. And then the minus 1 is after, huh? So what do you think that's going to be?
1 or negative 1.
That's no. You can't put 0. And you can't put negative in a log. It'll be an error. Yeah, if you typed it on your calculator, you type, let the top go top, let the bottom go bottom, minus 1. That'd be error. So let's try it now. Let's put in 1. Put in 1, you're going to get log base 5 of 1 minus 1. So let the top go top. Let the bottom go bottom. Minus 1, that's going to be 0 minus 1, negative 1. So over 1, down 1. Is that a true point on the graph?
Sure.
Right there. Look at it. It's beautiful. Over 1, down 1. Yeah, that's the real answer. If you did G, it would give you over 1, 0. And that's right here, and that's not a true point on the graph. B is the answer. We good with that? Good. See, everybody okay with how I made the table value? So that's why I showed you earlier about the making double log thing, because I wanted you to be able to do it when we were making tables. So is that okay what I did there? So when I plugged, so I took this I took the B function, and I plugged in a 1 here. And then to work this out, I took this guy and I let the top go top and the bottom go bottom with a bar between them. Hit the buttons on my calculator. Log of 1 is 0. Divided by, anything is 0 minus 1 is negative 1. So I got that value, negative 1. And then I found that, indeed, is on the graph. Over 1, down 1 is a point on the true graph. So B is the true graph, true equation, producing that graph. We good? All right, glad to help. So here we go. So log base 4 of x is 2. So we want to solve that. Want to solve that problem right there. So what do we do to get x alone? X is buried inside of a log function. How am I going to get that log off of it?
You do the inverse of a log.
And what's the inverse of a log?
An exponent.
Exponent. What base should I put? The same base. Yeah, 4. And these will cancel, huh? Is that making sense? So these are just inverses of each other. You got a log, you want to get rid of it, you do an exponent. You got an exponent, you want to get rid of it, do log. X equals 4 squared, which is 16. Want to try number 25? Same thing on 25? Same thing will work for you. Go to the first screen here. Okay, so how do we get rid of the log word? Do the 2 power thing. And that's the logs and exponents are opposites. Let's cancel each other out. So you get 8x plus 7 is 2 to the third. And 2 to the third, what is 2 times 2 times 2? 8, right? 2 times 2 is 4 times 2 is 8. And then you just subtract 7. 8x is 1 divided by 8. 1, 8. Easy as pie for you, right?
That's how you do it.
Good. On we go. That one.
Oh, 7. Like your observation.
All right, so how do you get rid of that log word?
X.
Same base, huh? In this case, it's kind of weird. It's an x, but that's fine. Totally right. These cancel each other out. So what does that give us? 49 is x squared.
7.
Yeah, and how do we turn that into normal x, you just root it. Now, when we root, we're supposed to do plus or minus, huh? Remember that? When you put a roof on, I always make the analogy, if you put a roof on your house, you're going to have to go, I'm going to have to get the ladder out of the garage and go up and down the ladder, right? I can't just jump on the roof. So I'm trying to remind you, when you put a root on both sides, you got to go plus or minus, up and down. So it's plus or minus 7. So x is plus or minus 7. But, having said that, see how x was a base? You can't, the bases cannot be negative. Bases cannot be negative. So really you get rid of, it's only regular 7. The answer is only normal 7. We don't keep the negative. Honestly, I'm not going to test you on that. It's kind of weird, like why can't bases be negative? It's kind of a long story. I'd be glad to talk to you about it office hours. I'm not going to test you on it, but just want you to know on this problem, bases cannot be negative. If that x was anywhere else, if that x was anywhere other than the base, I would let that negative answer stand. And we'll have one of those in a minute. Like 2 problems down the road or something. We'll have one where we do the root and we plus or minus and we keep them both because x is not in the base on that problem. But it's in the base here and you can't be negative in the base. Okay. All right, so what have we learned about ln? Natural logarithmic natural log. What have we learned about it? What's its base, I mean? E, right? Now, you think, well, yeah, there it is right there. No, actually, there's another E. How do I know? Well, that first E is on the level. It's not lowered down, is it? So that matters. It matters whether they lower something down or not. That E is just another E. There's a hidden lowered down base E as well. Does that make sense? Ln always hides within it a lowered down E right next to it. So I'm going to go ahead and show the other E for extra clarity. Now, what do you think happens?
Oh, then cancel it.
Yeah, these guys. Well, let me show you by way of analogy. Well, you could even look back. Maybe it'd be a long way back. Way back. This is like a review of our lecture. Real quick there. Yeah, look right there. Beautiful. You see what's happening? Well, actually, I want one with the log in the front. That'd be even better. Do I have one like that? Yeah, look right here. Look back to number 2. That's the first problem we did today. See what's happening right there? When the log base and base, that's also a base, they cancel, don't they? When those are the same number. Why? Because think about this x. He's both being raised to the 2 power and he's inside of a log base 2. Well, they cancel. So when the base and the base match, the log and the base is canceled. So fast forward, there's our lecture again. I should just do that every day. There it is. Okay, so what happens?
Everything disappears.
Those cancel when the bases match. So there's nothing to do here. It's just 15. X is just 15. The ln base E cancels the other E. That's the point of logs, huh? They're the opposites of exponential functions. The bases cancel the exponents. So there we go. Kind of a weird one. 28. Log base 3 of 27. Log base 3 of 27 equals x. Try that one. See what you think there. You know, you could just read the left side. If you're reading the power needed, could you do that?
Yeah.
Remember, log means power needed
To make 3.
on a 3 to make it 27. What power does 3 need on it to make it 27?
3.
Done.
Clear up.
Now, I'll do it more formally as well. But if you could just read that, read log as power needed, then you can see what the answer is. But I'll do it more to do it formally, I would have to get rid of the log word, right? How do you get rid of the log word? Do the same base, huh? And then they cancel. So 27 is 3 to that. See, there's the same thing we were looking at. 3 to what power is 27? See, it's the same question. So x has got to be 3. Third power, huh? Good? He's easy. Questions? Okay, try that one. You can do the power needed thing again. If you can just read that log on the left side, you could save some time. And then just solve for x.
So that whole side becomes that number, and
Mhm.
then it's set
That's right.
equal to that?
Mhm.
And then- Okay.
So, power needed on a 2 to become 8. 2 to what power would be 8? Be 3, huh? Because 2 times 2 times 2 is 8. All right, so 3. So if you can just read that, then you know this side's just 3. Equals 2x plus 5, and then you just solve it. Now I'll do it more formally. Let me go back. I'll do it more formally. So formally, how would you get rid of the log word? Just 2 power. And cancels, yeah, base 2, right? And then we get 8 is 2 to the 2x plus 5 like that.
But you'd have to make 8 into the same base.
Yeah, good job. You'd have to make that 2 to make both sides the same
To the third.
base. Yeah, 2 to the third.
It's pretty much the same thing.
It is. Yeah, it ends up being the same thing. And then you set the powers. There's a lot more steps this way, though. And then, right, because when the bases are the same, then you can set the powers equal. Then you solve for x. Subtract 5. Negative 2 is 2x. Divide by 2. X is negative 1. Either way, formal or informal, x is negative 1. Is that good? Questions I can answer? E to the 7x is 3. Okay, so and we want to solve for x there. So this is all about solving for x. In fact, let me just rewrite it. We got a little more room. 7x.
Ln both sides.
E to the 7x is 3. Did I get that right? Yeah. Number 30. Okay. Yeah. So we want to get x alone, but x is in power. This is like kind of how I started off the lecture today, right? I said, how do you, when you got x up there in the power zone, how are you going to solve for x? How are you going to get it out of power? You can't divide by the e. What are you going to do? And that's why they made up logs, huh? Because that's the inverse of. So whenever x is, so you want to remember this out of context. You know, next Thursday we take the exam. Everything's all mixed up. So you got to know something deeper. That's why I give you those practice exams to go over and over again. You got to know it kind of deeper to be able to realize out of context. Oh yeah, if x climbs into power, when x is up in the power zone, the way to get it out is log. So yeah, so I'm going to do log on both sides. So and when I do log on both sides, what base am I going to do? Same base, huh? Log base e. What's another way you could write log base e?
Ln.
Ln. If you want to write Ln, feel free. I'll change it to Ln on the next step anyway. But I just want to emphasize E, you know, same base. So yeah, so then these just cancel. And that's what gets rid of it. And this is just Ln of 3, huh? I'm just going to write Ln. That's what log base E is. It's Ln. It's the shortcut for it. Anyway, now that the x is out of power, it's easy to solve. What do we do now? You could do this years ago. How do you solve for x now? Just divide by the 7. Boom. There we go. Now, they don't want a decimal. They want just that right there. They say, the way they say it is they say, give me an exact answer. Sometimes you think the exact is the decimal, but that's not a right thought. Whenever you do decimal, the decimal goes forever, so you have to round it so it's not exact. So when they say exact, they mean we don't want to round a decimal, just give us the answer straight. So that's what they want, just that. All is well? Okay. You got x into the power zone, get it out of there. So I'm going to do, so the opposite of exponents is logs. So I do log base e on both sides. Cancels out. 3x plus 2 is, and that's natural log, isn't it? Log base e is natural log. So now what do we do to finish getting x alone?
Subtract 2 from both sides.
Subtract 2 from both sides. So then we get
For an exact answer.
3x is L into minus 2. Last step, divide by 3. Divided by 3, there we go. We keep that 2 separate. He's outside of the plug-in, huh? So just like that. That's the answer.
Beautiful.
Is it comfortable?
Yeah.
Couple more of these and we'll go back to those graphs. All right, I'll flash off that. Okay, so try that one. You got to get rid of that log word, right? So I'm going to do 4 power on both sides. That gets rid of the log, right? Powers and logs, or we just keep hitting that theme, huh? Exponents and logs are opposites. So then what do we get? X squared plus 6 is 4 to the third. That's 64, right? 4 times 4 times 4. 64. Now, how do we, so we got rid of the logs, got rid of the powers, we're just regular now. How do we solve for x? Yeah, a good question was asked in my last class. You know, previously, I said to you, whenever you have x squared, you're supposed to get a 0, huh?
No, you can't.
Yeah, in this case, it's a little different. So let me clarify. Let me give the rest of the story, as some commentator always says. Anyway, whom I can't remember his name now. Anyway, x squared, it's if you have x squared with x to the first power. If you have, and we don't have an x to the first power, huh? That's when you get a 0. See, normally we have an x to the first power here, and I would just get a 0, and then you would try to factor. Remember, that's the whole thing I talked about earlier. And or you could, yeah, do the negative b. I'm running out of room here. That's all if you have x squared and regular x. Negative b plus or minus the square root of b squared minus 4ac all over 2a. That's x squared with a regular. See, if I had a regular x here, or maybe there, then yeah, I would need to do all that. I would need to get a 0, try to factor. If it doesn't factor, use the quad. But if you just have x squared and no x to the first power, right? X squared and no x to the first power. That's easier. That is just get x squared alone and then put a root and a plus or minus root over the sides, huh? It's a little quicker. So that's what I'm going to do here. That's our situation. We just have x squared in numbers, huh? We don't have x to the first. So just subtract 6 from both sides. So x squared is, what's that, 58? And then you just root it, and when you put a roof on the house, up and down the ladder. And we will keep both of those answers this time. Because x is not a base, is it? Remember the other one when I threw out the negative? Because I said x can't be negative when it's a base. Well, this x is not a base. The base is 4. This x is not a base. So what's the answer to the problem then? It's root 58 comma minus root 58. They want both answers. You can't simplify the root 58 either. Remember simplifying roots? If you broke it down 2 times 29, 29 doesn't go anywhere. So we're done. We good there? All is well? All right. One now. And I want to kind of give you a general game plan now. We're getting a little bit harder. So, solving for x in the power zone. So how do you solve when x is up there in the power zone?
You get rid of the b. You get rid of whatever.
Right, but first step is get the base alone. And then log both sides with the same base. So first get the base alone. Then do the log thing, right, to get rid of that. So this is when x is up in the power zone. So I'm trying to help you remember this long term, because you're going to see it all of a sudden, not only on the exam Thursday, but then in the next section of the course, we'll be doing big old word problems, and they'll be exponential. Come down to the end, you'll have x in the power zone, and you'll need to remember, logs. And there won't be logs anywhere in the problem, So it won't like naturally occur to you. You'll just see x's in the power zone at the end of some financial problem or biology problem, and then you have to remember, how do I get that x out of power? Logs. So you want to remember this game plan. So when x is in power, first get the base alone, then do the log thing on both sides. Okay, so what's my first step then?
Just 2 power.
Divide by the 5. Yeah, because you got to get the base is the e, huh? So when I say get the base, so the base is the thing with the power on him. So the e is the base. So you got to divide off that 5. So that's my main point, is get rid of that 5 first off. And so then you'll have e to the 0.2x is 11 over 5. We good to there so far? So I got the base, that's step 1. I got the base alone. I got the e. The e is the base, so I could draw the arrow over there. So I got the base alone. And now what do? Log both sides with the same base. Is that good there? And then these cancel, don't they?
Mm-hmm.
So then we get... And log base e, that's just ln, huh? You good there?
Divide by 0.
Now x is out of power. Once x is out of power, it's a piece of cake, huh? Just divide by 0.2. 0.2.
Are you going to have to solve this?
And that's all they want. They want just like that.
Oh, just, okay.
Yeah, you can just type it in
Answer.
just like that. It's all about getting x out of power, isn't it? It's all about getting x out of power. So I used to always tell history stories because I'm a wannabe history teacher. Can I give you 1 minute of history?
Yes.
So it's all about, so I'm going to try to help you to remember when x is in power, because you're going to have to remember this out of context. When x is up there in the power zone, you get it out of power with logs, right? So it's all about being in power. So, one of the most famous, we're in math class here. All right, sorry, I'm probably going too far. I can't do 1 minute history. All right, so let's do this one, and then we'll be on to the graphs. Let me just write the formula for you. All we need there is that formula. P equals 760 e to the minus 760 e to the minus 0.145h 145h, and they're telling me P is 322. So on part A, P is 322. All right, so all I have to do for, well, it's not simple, but, so you can skip all those words. It's just all, a bunch of words. It's about a hot air balloon. It's a real life kind of interesting situation about a hot air balloon and how much pressure you put in the balloon to blow it up and the height the balloon will go to based on all that. It's a physics relationship. But in the end, we don't need all the words. All we need is the formula, and then they're saying P is 322. So that means I just stick in the 322 right there. So that'd be 322. 322 equals 760 e to the minus 0.145h. Good to there so far? And now, and they want us to find h, so I should have written that. Find it. So notice basically it's, if you put this much pressure in the hot air balloon, how high will it go? That's basically the physics, real life. I think it's interesting when it gets real. I like when math hits reality here. So here's a real life, hot air balloon. How much pressure you put in the balloon determines how high the balloon goes. So basically if you put 322, whatever it is, atmospheres of pressure, how high will the balloon go? Solve that equation for h. So how do I solve for h?
Do you log base e the e, or do you log base e the 760?
You first divide off the 760.
Okay.
Right? So this is my game plan. So this is what I'm hoping you'll remember even, weeks to come when we solve lots of real life problems with biology and economics. When the letter's up in the power zone, that's part of why I told the whole history story. Part of it is I just like history. But I'm trying to help you remember, when the thing gets in power, right? The problem with Hitler was he got into power. right? There's always crazy people with crazy views, but you don't want them in power. So when h gets in power, when the letter gets in power, what's going to get it out of there is a log. That's why they made up logs, for when they would have letters in power. So what's the first step? You got to get the 760 off first, huh? That's what I was saying here. Get the base alone first, then log both sides. So whenever x, or whatever your letter is in power, base alone first, then log both sides. Yeah, so my first step is to divide off that 760. And I wouldn't even use my calculator. I would just leave it, just as it is. It's totally fine. 322 over 760, e to the minus 0.145h. And what do we do now to do that? Is we log both sides, huh? So I'm going to do log base e, or you could just write natural log, same thing. Right? So whenever the letter's in power, you log both sides. We get the base alone, and then log both sides with the same base. These cancel. It's opposites. That's why they made up logs for this very purpose. And so that's ln, right? Log base e is ln, as you know, of 322 over 760 equals minus 0.145h. So, yeah, so divide. Yeah, now it's just divide. Now, once the letter's out of power, it's really not a problem. Once Hitler was dethroned, it wasn't a problem. Mussolini, well, anyway, enough of the history. Boom, there we go. H is alone. So there's our answer. We good? I want to go back to the graph ones. We have 10 minutes. So I'm going to do at least 2 of them. We good to there? Is that okay if I flash off that?
Yeah. Comes up to 5.
17. So these problems, 17 through 23, these 7 problems, is a pretty long but very valuable. They're going to tie all this stuff together for us. So hopefully we can get through 2 of them here. So the first thing they're going to ask us is the domain. So what's the domain? What have we learned today about doing the domain for a logarithm?
Must be greater than 0.
Yeah, positive only greater than 0, right? So you grab the inside and you say, okay, inside you have to be greater than 0, huh? For any log, the inside is positive only, not negative, not 0. Positive only, x greater than negative 5. Okay, next, part B, they want us to graph. Okay, so let's graph.
If it has to be greater than 0, how can it be less than 0? It must be greater than negative 5.
Right?
Yeah.
Anything greater than negative 5.
Okay.
Yeah, it's totally good.
Great.
Okay, so now let's graph it. Okay, so when we go to graph this thing, how do we start? Where's the vertical asymptote? Remember, logs always have a vertical asymptote. Where's the vertical asymptote? It's the opposite of the number next to x, huh? Because remember, x is always opposite. We learned that for a long time ago about x effectors, right? They're always opposite. So if there's a plus 5 next to x, it'll be back here at negative 5. 3, 4, 5. So at negative 5. We have a vertical, and then this is a normal log graph. There's no flips or anything, so I'm just gonna, it goes up to the right, huh? Like that. We good? So there's the graph. That's good enough for multiple choice, just like that. Now, on part C, they're going to ask us to, where am I at? Okay, part C is going to say find the inverse. So now's where we see everything tie together really nicely. How do you find, a couple sections ago, I think it was maybe last Tuesday, we did inverse functions. Had a whole section on that. So how do you find an inverse function? What do you do? There were 2 steps. Remember those 2 steps? What's the 2 steps? Step 1, switch or invert x and y. That's the main thing with an inverse function, is a switching of x and y. And then step 2, solve for y. Remember that? You switch x and y, solve for y. That's how we did it last week. Good little review here. I hope that quiz you just did helped you review a little bit. Quiz number 3. So switch x and y, solve for y. So I'm going to take this original formula up here, and I'm going to switch x and y. Now, I don't see y. Where's y? It's the f of x. Yeah, remember how we talked about function by common agreement in the math science world? F of x, g of x, that's y. So I'm going to switch it, so that'll become x out here and y in there. Is that okay? I just swapped these guys. They just traded position. So the function values are y, and when you do an inverse, it means to invert, switch, x and y, and then solve for y. So that, which means, you know, we want y saying I want to be alone. Solve for y. Get y saying I want to be alone. Get this natural log off of me and get rid of this plus 5 that's next to me. I want to be alone. Solve for y. So what do I do to do all that? What do I do first to get that natural log off of him? Yeah, good. Because really, there's an invisible, understood, lower down e. Now, every log has a base. Natural log has an e, huh? And so how do we get rid of logs? The opposite is inverse. The inverse is exponential. Yeah, that's been the theme of the day, huh? Logs and exponentials are opposites. Yeah, that'll cancel that out. And that'll give me e to the x is y plus 5. And what do? Just subtract the 5, huh? So e to the x minus 5 is y. And guess what that is? That's the inverse function.
So they don't want you to graph it.
And then they want you to graph it. Yeah, they want everything on these. Everybody good so far? So first off, we see a major connection there. The steps we learned about how you find inverse functions, switch x and y, solve for y, lead to the fact that a natural log base e, his inverse is an e function. That proves it's really true. That logs and exponentials are inverses. We just went through the steps of finding an inverse and bang, there it was. It's true. Now let's go to the graph. So we could put it on the same axis. So when you graph an exponential, right, we learned last time, did homework last night, graphing exponential, you always have a horizontal asymptote, the number added off to the right or add or subtracted on the right. So what's the horizontal asymptote? Negative 5. That's our horizontal. So that right there is our horizontal. And so this is our inverse function. So horizontal is at negative 5. 1, 2, 3, 4, 5. Right there, we have at negative 5 a horizontal asymptote. See how that perfectly corresponds with the vertical at negative 5? And then let me graph the exponential. Now, what do exponentials always do? They come down for a landing on their horizontal and rocket up to the right, unless they've been flipped or something. And this has got no flips. No negative on the x, no negative in front. So it's just going to go upright. So it's just going to go here and just go upright. I'm not the best drawer. That looked kind of shaky in there. There's my art career troubles. I told you, right? I got a C in art in 7th grade. And I was trying. That was the end of my art career. All right, so anyway, there it is. And look at how they are a perfect reflection across the diagonal. I mean, I didn't draw it too perfectly. But see how they're a perfect reflection? Remember, inverse functions are always a reflection across the diagonal? See the perfect agreement with everything there. Last question, they'll ask, what's the range of the original function? The purple one. Remember how you do, we already got the domain of it right here. There's the domain of the original. Range is how low and high the graph goes, huh? How low and high does the purple graph go? All the way down, all the way up, huh? Negative infinity, positive. It won't always be that, but it is on this one. We got 3 minutes. I want to set up like maybe one more. So step 1, let's find, part A, I mean, what's the domain? How do we find the domain of a log function? Take the inside and say, hey, inside you got to be greater than 0, positive only.
Must be greater than negative.
X is greater than negative 3. Piece of cake. Let's go on from there. Part B, let's graph it. So I want to graph that function. So where is his vertical asymptote?
Negative 3.
Yeah. 1, 2, 3, negative 3.
The horizontal is negative 1, isn't it?
So negative 3 like that. We good? And this one doesn't have any flips. There's no negative on the log, no negative on x. So he's just going to, go up to the right. And he always takes a dive. They always take a dive at their vertical asymptote, right? Okay, now the part I really wanted to, I rushed through that pretty quickly. I really wanted to help you with the find the inverse thing. That's the part where I think it'll be more challenging. Let's find the inverse. Remember how to find an inverse. Step 1, you switch x and y. Switch x and y. Step 2, solve for y. So can you do that? So take, this is y out here, right? This is y right here. The f of x is your y. So try that. See if you can do that real quick with our last minute here. Switch x and y. So that would put the x out here. And the y right there. Like that. And we want to solve for y. So y is over here saying, I want to be alone. Get this log off of me. Get this 3 and this -1 out of here so I can be alone. So what do we do to do all that? What do we do first is really important. Add the 1. Yeah, because remember you got to get the log or the base thing alone, right? So you got to get rid of that 1 first. Add the 1. X plus 1 is log of y plus 3, right? Like that. So you always get the log or the base or the whatever alone before you do the opposite thing, the inverse thing. What's the base on that log really?
10.
Oh, good. Good. I was going to say E. It's not E. It's 10. Good job. Yeah, if it was the ln word, that's base E. If it's the normal log word, it's base 10, huh? Mm-hmm. Good job. Yeah, if it's the normal log word and it's not showing a base, it means 10. If it's ln, it's always E. Yeah, so there's really an understood invisible 10 there. I'm going to show it for clarity. So what do I do then?
10 both sides.
10 both sides. So I go 10 this side, 10 that side. These cancel. So 10 to the x plus 1 is y plus 3. Subtract the 3 over. 10 to the x plus 1 minus 3. There it is. There is the inverse function. You can graph it and do the rest. There it is. Oh.